see later on as well, that seawater density and salinity and temperature are characteristic of different oceans. And there's these lines of equal density, what is called, don't worry about what it means, isopycnals, contours of equal density anomalies. That's just the way of demonstrating it, but what we'll see is how you can identify different water masses in terms of their temperature and in terms of their salinity. Because different water masses have different combinations which make them behave in different ways. So we could start with a sort of average point. I'll go back to that because it comes up again now. So we can identify sort of average salinity, average oceans, so 35 PSUs, about average ocean water, is somewhere, suggests that this sort of should be the temperature, and this is the density anomaly that we've actually got within there. So we'll see that later on when I demonstrate some of the ocean characteristics. So we can also do the same as we've done with air masses when it comes to looking at other characteristics. We talked about pressure and temperature, but if you assume uniform depth and temperature and you look at salinity effects, high salinity, high pressure, low pressure, movement will be from high to low, and the same will be true. We can always sort of look at the differences, and we can predict, if we assume certain uniformities, certain constancies, how the ocean mass will move. What this means is that if we make some assumptions about temperature or depth or salinity, we can assume certain pressure gradients, and those pressure gradients will drive the movement within that fluid. What the problem is, of course, with oceans is that they are three-dimensional and they go with depth. And you can't, therefore, assume that what you see at the surface is exactly the same as you see with depth. And modelling the ocean, therefore, is very difficult. For instance, if you looked at any part of the ocean, of the deep ocean, you can guarantee almost that water flow will be in one direction at the surface and probably in an entirely reverse direction at depth. And maybe in either direction at intermediate. So we have surface water, deep water and intermediate water, and often these will be behaving in different ways because they have different densities and different temperatures and different salinities. So if we look at a temperature gradient, let's start with the easy one. Polar comes down here, virtually uniform. It's actually colder a little bit near the surface. Why, if it's below zero, isn't it ice? Salinity. It's actually, the saltier it is, then the lower the temperature it will freeze at. So there is a key element here between the two. So polar waters tend to be, in general, have a uniform. At the other extreme, the tropics can start with a very high temperature. Do you know what the key temperature is for tropical water to generate hurricanes? 26 degrees. Anything above 26 degrees is a key component for the potential for hurricanes. So we can see we're in tropics going consistently above 26, so that's why hurricanes form in the tropics. But we can see that there's a very steep gradient, very severe thermocline, very rapid thermocline of dropping in temperature before it sort of stabilizes down after about somewhere around 500 meters. And in the mid-latitudes where we're at, has to be the height of summer off Cornwall for 14 degrees centigrade at the surface, but we can see it sort of drops off such that most of the bottom water in the globe is somewhere around 5 degrees centigrade. So most benthic lower water is, despite where it's come from or where it is somewhere around the same depth, around the same temperature. Salinity is very different in the way it changes. So in the tropics, salinity peaks just below the surface and then stabilizes down to this average value. And you can see 35 PSUs is about the average value. Salinity in the mid to high latitudes starts very low. Why is salinity low in the high latitudes?
You've got the ice melting.
Yeah, you've got ice melting, fresh water. You've got ice melting. Also, you've also got some big rivers coming into the Arctic as well, from both from Canada and from Siberia. That's freshening up this, making low salinity. And that's low. What does that low salinity allow? Sorry?
Freezing.
Allows freezing. So low salinity water will freeze much more easily than high salinity water. So you've got this, in a sense, double whammy. That as long as you've got that fresh water going in, it will freeze, or potentially will freeze. But quite rapidly, that gets up above 34 and then stabilizes. And in the subtropics, slightly higher salinity. And you can see it sort of, again, coming down with a shallow. These are average values for these general areas. And density, which is a function of temperature and salinity, so it's those two integrated together. You can see at the equator you have low density water across a range of, and then it all goes down to a same temperature, same density. Tropics, high latitudes, starts denser and then goes down as well. So we have this sort of variation, but this in a sense integrates the temperature and the salinity. Those are generalizations, real generalizations about the ocean as a whole, but they move about, so they mix. They're mixing processes, the salts are mixed up. If this was the only processes, and that's a spelling mistake, it should be affecting, the concentration of dissolved solid, the oceans would have a uniform salinity. In other words, everything just goes in, nothing else happens. They don't. Salinity varies considerably, and this is the spatial distribution of salinities, with high salinities nearer orange and red, low salinities being blue. So we can see that the northern latitudes have much lower salinity than the southern latitudes off Antarctica. So we can see differences between the two up there if we see it. We see these high salinities, especially down here. Why is that very high there? Why has this got very high dissolved salts in this part?
Atlantic Ridge.
Sorry?
It's the Atlantic Ridge.
It's warmer.
No?
It's in the middle, so it's like less mixing of water from fresh
Possible,
water
but no.
sources.
Where do all these elements come from that get into the oceans? Again, I did this with you in the first year, you forgot it. I showed you a picture.
Is it wind transportation?
Where from?
Sahara?
Sahara. This is all Saharan dust, which whips up the Dealey Depression, piles into here, and is heavily concentrated in that area. This is where you fertilise the oceans. Same is true for off here, because we have very dry area along the western part of South America, again to be picked up, quite high around Australia because there's quite a lot of sediment available here. And we see this very high Mediterranean. You know, the Mediterranean is very salty, largely because the water doesn't exchange very much, but there's plenty of salts getting into it. So, and then it's evaporated off as well, so it's wonderful, warm and dry. And you can see these odd places where there's high salinity. Another place you might get it is where you've got a lot of sediment being brought into the oceans from big river deltas. So we can see that we've already got these differences in salinity. And they begin to look also somewhat similar to our atmospheric structure. It's as if there are cells, concentrate, which seem to very similar to the sort of cells we see over the Atlantic. This one here, this seems to mirror the ENSO area, the ENSO region, and the relationship to the southern hemisphere Hadley and Ferrell cells. So salinity variation, more salinity as evaporation takes place, obviously, and low salinity where you get more condensation and more precipitation. So we also not just have the source material, But we also have the categorization that if you've got general evaporation taking place, especially in the warm areas, you will get greater salinity in the surface of the water, in the surface water. So as long as P is less than E, precipitation is less than evaporation, salinity increases. P, precipitation greater than evaporation, you get salinity decreasing. And we know, we've shown this is the difference between precipitation and evaporation. So what this shows is that it's not just a function of available sediment, but you've got to get the available salts coming into the ocean in the first place, but it's also a precipitation-evaporation balance that gives us the actual values and the high variations. What you can see here is that you've got very, very high precipitation, and if you compare that to the salinity map up there, you will see these areas with quite a lot of precipitation, very green, and that's very blue, therefore we do have low salinity. So despite the fact that we have some of the biggest sediment-laden rivers in the world around there, we have an awful lot of sediment being moved, the basic atmospheric conditions manage to sort of overcome that and change the actual pattern because we've got such high amounts. Surface temperature of the oceans is more straightforward and seems to basically be generalized as you might expect. You get variability, but you do get quite a sort of pattern which is latitudinally affected. But of course that's a generalization, varies, and you begin to see some patterns within that, as we'll see as we go through. So a few technical terms before we look at water masses. Salinity, changing values with depth is a halocline, equal values isohalines. Temperature,